Hi, so my name's Bradley Emmy, and I'm a senior at Viewpoint School, and today I'd like to talk to you about cryptography, which, as stated, is the science of information protection, and basically, it's the science of making codes. Now, historically, cryptography has used many languages. People have been making codes for as long as humans have existed, and we've used languages like Navajo and Japanese. But today, in modern cryptography, we use the languages of math and science. And this is for one reason, because codes based on math and science work even if the person trying to steal your information knows exactly how you're making the code. And before I get into the details of how people actually make these codes, I'm going to talk a little bit about why cryptography is important. Well, we see cryptography all around us. Every time you make a bank account transfer, every time you log into Facebook, every time you accept a privacy policy that somebody emails you and may or may not read. These things are all applications of cryptography. And so today I'm going to talk to you about two very cool methods of cryptography. One is based on math, and one is based on physics. And hopefully, I'm going to debunk your perception that privacy and safety are these huge threats to us, and that these are things that we really, really need to worry about, and that we're actually quite safe. The first cryptography system I'm going to describe is a system based on math. And I'm going to use this analogy to paint to kind of explain to you how cryptographers get the problems that they want to make these codes. So for instance, in this analogy, Alice and Bob each start with a common paint. They then add their secret color to the paint, and then they switch mixtures. And then they add their secret color again, and they have a common secret color of paint. And the reason this works is because there is an easy problem in this diagram and a hard problem. The easy problem to make the code is to mix the colors together. It's very, very easy for Alice and Bob to mix two paints to get a combined paint. But it's very, very difficult for someone trying to intercept the message to split that paint into two different colors of paint. That is, there's one easy problem, that is mixing the paint, and the hard problem, separating the paint. And these are the types of problems that cryptographers want when we're thinking about how to make codes based on math. We want problems that are easy to make, but very difficult to solve. And the problems used in industry include the factoring problem, because it's very, very easy for a computer to multiply two numbers together, but very difficult for a computer to split those numbers apart. Another problem is called the discrete log problem. It's very easy for a computer to do exponents, but very, very difficult for a computer to do logarithms. But there is one problem with this system, and that is it's based on computing power. Computers, as seen in this diagram, are getting much faster and faster over time, and eventually, not in the near future, but in the very distant future, we'll have a computer that will be able to actually break these kinds of codes just because it's so fast that it can run guess and check so many times over that it'll eventually solve the problem. So the solution to this problem is not a solution that is based on math, but one that's based on physics. And I'm about to describe this system right here. And it actually relies on the amazing properties of quantum mechanics. So in this diagram here, Alice is sending not numbers to Bob, but Alice is actually sending photons of different polarities. And photons are just little packets of light. And to see why this system's secure, let's try and understand why Eve would not be able to break into this system. So Eve could just take the photons that Alice is sending to Bob. But then Bob would know that, well, he's not getting any photons, and then he would just try a different channel. Eve could also take a photon and try and clone it, and send the clone to Bob. And then Bob would think that it's actually Alice's photon, but it's actually Eve's. But surprisingly, and this is what's amazing about quantum mechanics, is that that's impossible by the laws of physics. Quantum mechanics has this really cool property called the no cloning theorem, which basically states that Eve cannot take the photon and clone it, because photons have these things called wave states. And if Eve were to actually try and copy the photon, Eve would be changing the wave state of that photon in the process. And it would be impossible for Eve to clone the photon, therefore. So basically, this system is completely secure in theory. So I'd like to talk about some of the problems in experimental quantum cryptography, and then we'll kind of see where cryptography is going and why this is the cryptography of the future, because it's 100% secure. It's not just based on the fact that you have a really, really powerful computer. So this is actually a real article that I just pulled up last night, and this is actually solving the problem of distance. One problem in quantum cryptography is that it's very, very difficult to send photons over long distances, because A, if you're far enough apart, then you'd actually be having to send those photons through the Earth. And second of all, you wouldn't know whether the light is coming from my laser beam or whether it's coming from, say, the sun or other outside sources. So what this company is doing actually is they have this plan to actually launch satellites into outer space, and then we'd shoot the lasers, the photons, off of those satellites from Alice to Bob. And another problem that, that quantum cryptography has is that it's really expensive, unfortunately. So right now, how people actually get those single photons to send in the channel between Alice and Bob is they actually shoot lasers through a series of artificially manufactured diamonds to get the beam to split just right. And these are the types of problems that are going in quantum cryptography. But again, it's really safe and really secure because any eavesdropper can't break into the system without breaking the laws of physics, which is impossible. So in a sense, soon enough, information privacy will not just be something that relies on the goodwill and the trust of companies like Google and Facebook. It will actually be a right. It'll be a guarantee for us. And I hope that this kind of cryptography convinces you that math and science are tools that cryptographers use to make the world, to make the internet a little safer than you might have previously thought. And I'm going to leave you with this comic from my favorite webcomic, XKCD. Thank you so much for your time, and I hope you all have a great day. Thank you.